which will be presented by Clément Allain on Zoo, a framework for the verification of concurrent OCaml 5 programs using separation logic.
Can you hear me? Is it okay? So, hi everyone, my name is Clément Allain. This is joint work with Gabriel Scherer. It's my pleasure today to present this work in a very impressive place. This is basically the result of my PhD. So the story is the following. At the start of my PhD in 2022, the fifth version of the OCaml programming language was released, OCaml 5, in December 2022, to be more precise. And well, this version introduced parallelism and concurrency into the language through a number of new mechanisms. And then, reacting to that, the OCaml ecosystem developed a number of new concurrent and parallel libraries, including domain sleep library, which provides a standard scheduler for OCaml, the Saturn library, which provides standard log-free algorithms, and also, among others, the Eio library, which provides support for asynchronous I/O. And, well, obviously, given this new software, new tricky concurrent algorithms, we need to apply formal verification, obviously. So this is the motivation. Our motivation is to this work, verify real-life algorithms using state-of-the-art techniques. And, well, at the start of my PhD, the most natural things to do was to use the heaplang language. So this is the canonical Iris language. It's mechanized like Iris. So by the way, Iris is some of you may know it's a very powerful separation logic. I claim that it is basically necessary to verify the kind of algorithm that I want to verify. So for me, it's like a constraint. So I needed a language that supports Iris. So heaplang was the natural choice. However, our experience shows that it is, well, a bit limited when it comes to verifying real-life OCaml programs at scale. So basically, this is the starting point of our work based on the fact that the abstractions in heaplang and also some incompatibilities that I will talk about were not ideal for verifying the programs that we wanted to verify. So we developed the Zoo framework for verifying concurrent OCaml programs, and now I'd like to give a brief overview of this framework. So the idea is the following. Say you have some OCaml code, say you have a joint project, and you want to verify the libraries in this joint project, so you can call this tool OCaml to Zoo, and well, it's actually a transpiler. It will translate the files, the OCaml files, basically the project, into Rocq files containing Zoo code, which is a language deeply embedded inside Rocq, and then you can use the Iris separation logic. Now, concretely, so you have this joint project. Say you are implementing the domain sleep library, so scheduler, a parallel scheduler, and this domain sleep library relies on the Saturn library. Then calling OCaml to Zoo on this project yields the following hierarchy. So basically, for its ML file, you generate corresponding Rocq files, one for the Zoo codes, one for the Zoo representation of the OCaml types. Actually, Zoo, like heaplang, is an untyped language. It's untyped because we need to deal with unsafe features, and basically we can't be typed. Now, zooming on the stack module. So actually, the stack module implements a concurrent stack Great. So actually, it's the triple stack that Alexander has already mentioned and already presented. So the idea is that you have an atomic reference and you update it using component set. So for instance, here you have the push function. This is the OCaml code, and calling OCaml to zoo yields the following zoo code. Overall, it's pretty similar to the original code. I hope you will agree with me. Some little differences are due, I would say, to the current state of language and embedding inside Rocq. So anyway, the code in particular is pretty readable, so it can be reviewed to check for the consistency of the generated code. And so then, to show how you verify programs in practice, once you've entered the Rocq world, well, the real work starts. That's when you want to write specifications first. So, for instance, this is the way you would, the standard way you would specify the push function for the tribal stack. And, well, this is, again, like Alexander mentioned in his talk, this is a so-called atomic specification, iris atomic specification. So basically what you're saying here is that you are logically updating the stack from VS, some value VS that you get at the linearization points of this function. You're updating the stack from VS to VS plus V, so basically you're atomically pushing the value V, and this is more or less equivalent to showing that this push operation is linearizable, as is standard in the literature. Okay, so now to wrap up this global overview, here are the features currently supported by Zoo. In particular, note that you have the high-level abstractions like ADTs, records, and mutually recursive functions. Those things are not supported by HipLang. This is the kind of things that brought me into developing Zoo. And also, it supports physical equality. I will talk more about that in a few minutes. Also, another part of this work, I would say, is contributions to the OCaml language itself. So indeed, with Gabriel Scherer, we developed a number of new OCaml abstractions, OCaml features. So atomic references are already there in OCaml 5. We added atomic record fields. I will show what it looks like in a few minutes. Atomic arrays, and also so-called generative constructors that I will also present soon. Okay. Now, here, I don't have time to go into much detail, but I would at least try to convince you that this framework is practical. I hope it is. So here are a few things that we've verified, a few verification contributions, we said. So inside Rocq is the Zoo framework. Inside Zoo, we verified standard data structure, so more or less a subset of the OCaml's stdlib. So in particular, some sequential and also some concurrent modules. And then we've also added some here in pink. Then we've also verified persistent data structures, in particular arrays, stores, and union-find algorithms. And here I would like to thank Clément and Gabriel Scherer for developing the persistent store library and suggesting me to verify it. Also, we verified the RC of the module, which is basically a parallelism safe file descriptor that I will also present in more detail. And I would like to also thank Thomas Leonard for developing this, EIO and in particular this module. This RCFD module comes from the EIO library. It is interesting in several respects. So actually, Thomas Leonard suggesting verifying this data structure because of its quite intricate concurrent protocol. But as we'll see, it is also interesting, so we found, for introducing, for justifying generative constructors. Last but not least, we also verified a library of standard log-free data structures. Again, I would like to warmly thank Vesa Karvonen and Karin Morel, the two developers of the Saturn libraries. Saturn libraries. This algorithm comes from the Saturn library. So in particular, we verified, so actually we've not verified all algorithms, it's future work. We verified stacks, queues, different kind of queues, lists, array, and stack based. Okay, so this was the overview of Zoo and the different contributions we've made. Now for the time I have left, I would like to focus on a subtle aspect that we've worked on. So physical equality. If you program in OCaml, you may already be familiar with this. So in OCaml, this would be the equal operator, physical equality. And the question is, why am I talking about physical equality? So I claim that physical equality is ubiquitous in concurrent programs. Why is that? Well, again, consider the triple stack, an atomic reference pointing to a list, an immutable list. When you create the stack, this is an empty list, and then you want to, in the push function, you want to atomically update this reference, atomic reference, using the atomic primitive comparent set. Okay. So you read the reference, you read the content, you construct the new list that you want to update the reference to, and then you try. You try to atomically update it using the comparent set primitive. And well, if it works, you're good to go. Otherwise, you start over. Okay. So physical equality lies here in the atomic comparent set primitive. Why is that? Well, because you don't want to apply structural equality. It's too slow. So you want a fast test, a fast check to see, to compute whether you've seen the same content. Okay. So now I claim that in OCaml, so we have found in our work during the verification of, in particular this algorithm, but others also, we found that it is underspecified in OCaml. In particular, I claim that the current documentation is not sufficient for, it's not precise enough for verifying this standard simple data structure, the triple stack. Also, in heaplang, the formalization, the way physical equality is handled is basically incompatible with OCaml. So in particular, it is too restrictive. For instance, you cannot write this data structure as it is. And so the question is, can we do better? And the answer is yes. And so we present a new formalization of physical equality that we hope will influence the way it is documented in OCaml. So now let's see what can go wrong. So first, let's study the case when physical equality returns true. So when it returns true in this precise algorithm, in the tribal stack, so the most important point is the component set call. So say, you have the invariant of the stack, and what you want to do is atomically update the content, so VS. So atomically, you observe some values VS, and this is the current content of the stack. Okay. You call component set, and in the branch that is interesting here, in the branch where physical equality, which lies underneath component set, returns true. What you know in OCaml is that not only you have actually updated atomically the content of the stack, but also you've seen the VS, the values that you've observed, is physically similar to the old values that you observed in the first place. Okay? So this looks good. But then what you really want to say is that given that, you can have this. So you want to say that old and VS are actually the same thing, so that in the end you get the standard specification. The question is it true? Well, it appears that it's not. And to see why, we have to consider several phenomena. So first, sharing. So this is a standard thing in OCaml. Basically, immutable blocks, including concerns, are represented in memory as immutable blocks. And basically, the compiler and the runtime, for instance, through hash consing, might or might not choose to share these blocks. So sharing means basically giving the same actual memory block to some abstract immutable block. Okay, so this means that in OCaml, you may observe, as shown by these two tests, you may observe either true or false when you test equality of two syntactically similar lists. So you don't have that equality in Rocq over the abstract representation of values, particularly the immutable blocks. You don't have that equality in Rocq implies physical equality in OCaml. Now, this is quite standard. The big problem comes when you consider also value representation conflicts. So usually when you program in OCaml, you cannot observe these conflicts. Why? Because you're typed. The program is typed. So for instance, you cannot compare false and 0. You cannot compare booleans with integers. Except you can sometimes. You can, for instance, through this any type, which is basically an existential type. And basically this type, this any constructor in particular, so this immutable block, hides, basically erases the type. So when you call physical equality, this double equal comparator, things happen. So in particular, what the compiler sees is actually the physical representation of false and 0, which is actually the same thing. And so through sharing and these conflicts, you may get, if sharing is enabled, true for all these tests. So this means that physical equality in OCaml, in OCaml, physical equality in OCaml does not imply equality in Rocq. You don't get that the abstract value that you have in the verification, in the verified program are actually the same. So you cannot deduce that old and VS are actually the same. And so all you can do, given this behavior, this phenomena, is verify a more imprecise specification, basically a specification modulo, where you reason modulo physical equality. You only update the stack with a value that is physically similar to the former values. Okay, so this is the case when physical equality returns false. Now, the case when physical equality returns, this was the case when physical equality returned true. Now, in the case where physical equality returns false, this is also interesting. So actually, if you look in the OCaml documentation, you can read that basically in this case, you get no guarantee. No guarantee. And I would like to show in this second example that this is a problem in practice, including for functional correctness. So here is an extract from the code of the RCFD module that I've mentioned. So the parallelism safe file descriptor implemented by Thomas Leonard. What happens here first is that we're using our atomic record fields, the fields that we've introduced in this work. So this takes the form of this atomic annotation. Here you're declaring this field as atomic, and then you want to atomically update the state fields using the new atomic.lock primitive that mirror the standard atomic primitives. And also we have a construction to this atomic.lock construction to actually get the field and then have a type nice type for the comprehensive primitive. Anyway, so I claim that okay. First of all, I should briefly say what the story of this data structure is. So basically, what happens here is that we have a state type, state ADT, and this says that the state is either open or closing. Okay, either open and closing, and so at the start it's open, and then it gets closed. You switch to closing, and it's the end. You only get closing afterwards. And then I claim very briefly that what happens is that in the case where physical equality returns false, you have a problem because you want to argue that you have observed a closed descriptor, although it is not because of a particular phenomenon that is unsharing, which is a theoretical concern, but also, according to experts, may really happen in practice. So now, briefly to wrap up, first we have introduced generative constructors to handle all these problems. I don't have time to describe it, but it's in the paper. And to conclude, here are a few ideas for future work. More features, also coupling with semi-automated verification and relaxed memory. I don't have time, but thank you.
So we have time for one quick question. So have you tried applying these techniques to other languages, or is it very focused on OCaml?
It's very focused on OCaml, and this kind of, this is like surgery. We've looked deeply like what does this precise notion, physicality, means in OCaml. It would be a bit bold to speak about other languages. I guess that in other languages where, in garbage collected Java, say, languages where you have immutable values, this may also happen.
Let's thank the speaker again.